In this screencast, we're going to learn the essentials of what we need to know about vector components for physics. I know this is a topic that you've already learned in your math classes, but this is going to tailor our needs for physics in particular. What we can see here in this picture is a particular vector, F, representing in this case force. A force. Now, it's oriented at an angle, so it's difficult mathematically to deal with. In this vector addition model, this is the perspective we're using for the vectors, vector addition, which we've spoken about before. We have this vector, and it's easy to add x's and y's, but when they're at an angle, it's difficult to add them mathematically. So what we do is we take this force and break it into its horizontal or x component and y component. In other words, we turn this one vector into two vectors such that if they were added together, they would equal this. Fx and Fy are mathematically easily to deal with. F by itself is not. So for that reason, we take forces and break them into components. Looking at this from the perspective of the parallelogram method, one can see that taking this force and viewing doing the mathematics to find this component and this component really makes no sense. It doesn't make any sense to visualize it this way. So this is yet another reason why the parallelogram method is frowned upon and not used for very sophisticated physics. So this really is the method. To find these components given this F using the parallelogram method, you actually wouldn't. You would redraw it this way and do it this way. So let's take a sample. A sample type question that we would view. Two-dimensional vector components. Now, one-dimensional vector, it doesn't make sense to have components because it's already in only one direction. So by definition, there would be no components of one-dimensional vectors. So in this case, we have a two-dimensional vector. So we have a boat traveling at 13.8 meters per second at 52.6 north of east. All right, so what does that mean on this framework? First of all, we want to label our cardinal directions. So here is north, east, south, and west. Now this depiction here is not of space, but rather only showing direction. There is no where on this. This is not a map with northeast, south, and west. This is just where directions are oriented. And we'll see a little bit more why they're making that distinction here right off the bat. So here we have a boat at 52.6 north of east. Now if you notice, a 45 would be right across the diagonal, so the angle's a little bit more. And we see then that this angle is 52.6 degrees north of east. Now, north of east, again, we said before, this is east, so I would swing my angle 52 degrees toward the north, so that's the north of east. The components is the next thing we want to consider. So drawing the components, we will first drop this down like so. So there's the vertical component, which would have an arrow on it, like so. And the horizontal component would be like this. This is V, the vector V. This is Vy, and this is Vx. So what we can see is that when we have this velocity vector V, we can break it into its x component and its y component, and if we added Vx and Vy, we would end up with this overall vector V. Now, interestingly enough, I drew the same vector down here to illustrate a point that I was making before. And if I were to break this down into Vy and Vx. This angle here, also 52.6 degrees. We can see that the magnitudes of Vy in both of these places are going to be the same, and the magnitudes of Vx are going to be the same. Now, in terms of direction, wherever we are located, in this particular location, this direction is north. So we would say Vy is north, just as we would say here, Vy is north. Here we would say Vx is east, and here Vx is east. So you can see that it doesn't matter where I draw V in this space, in this field, I'm going to get exactly the same magnitudes and the same direction. So it doesn't matter where I draw it in the space. So that's the first point that I wanted to make. Now getting to the question, what are the northward and eastward components of the boat's velocity? Well, one of the interesting things here is that we've got, since these are vectors, we have magnitude and direction. Since these components are already drawn on the coordinate plane, we know the directions. Vx is east and Vy is north. It makes it very easy to deal with because there's no angle involved. So now it becomes a matter of finding out the sides of those triangles. So in this particular triangle here, we recognize this as the hypotenuse, and this as the opposite side, and this is the adjacent side. So to find Vx, we are involving the adjacent side and the hypotenuse. V is given, and it's given as 13.8. So we know this side, we're looking for this side, and we know this angle. So adjacent hypotenuse is cosine. So we have cosine theta equals adjacent over hypotenuse. Cosine of theta is Vx over V, and Vx then is V cosine theta. V is 13.8 and theta is 52.6. So we see that Vx is 8.38178 meters per second. Going back to our original data, we have 3 significant digits, 3 significant digits. So our answer will be 3 significant digits. So Vx with the proper significant digits is 8.38 meters per second. That's Vx. But this is just the speed. So Vx is meters per second east. Now, to resolve the vertical component, the vertical component y we are looking for involves the opposite, and we have the hypotenuse, so that would be sine. So we have sine of theta equals opposite over hypotenuse, and sine of theta then is Vy over V, and Vy equals V sine theta. Vy then is 13.8 times the sine of 52.6. So Vy is 10.96292 meters per second. And again, 3 significant digits in the primary data. So we're looking at 10.9, the 6 causes that to round up, so we're looking at 11.0 meters per second, and it's Vy, that's north. Those are the components: the magnitude and the direction of the velocity in this particular case. Now let's see why we do that. We do that so that we can add vectors. So let's imagine now we have a projectile kicked horizontally off a cliff at 5 meters per second. All right, so it's horizontally kicked off at 5 meters per second. And had been falling for 3.25 seconds before impact. What was the impact velocity? So we recall from our projectile motion that the object is moving horizontally at a constant speed 5, but as it free falls, it gets increasingly faster and faster and faster and faster. So what we have is a y component, a vector component, that has some magnitude, which we're not given. And the two of those will yield a final overall impact velocity. Most of you said and saw, realized, commented on the fact that an object that is dropped should hit the ground with a lesser velocity than one that has been kicked sideways. And you're correct, the speed is actually higher in that particular case. So we can actually find out that true impact velocity. And the velocity, of course, will have magnitude and direction. So in this particular case, we are also looking for theta. So Vy is the key here. If we write a model for the velocity in the vertical, we have Vy equals AT plus V0. It's kicked horizontally, so V0 is 0. So Vy is negative 9.80655 t. Well, we know t is 3.25. That gives us a vertical velocity of negative 31.8712875 meters per second. And now I'm going to store that value as y. So now you can see I know this side, and I know this side, and I need to find v, and I need to find theta. So I could do them in either order. Let me find v first. Perhaps the best would be the Pythagorean theorem to find that. So we have a squared plus b squared equals c squared. And the a side is vx squared plus vy squared equals v squared. This being the hypotenuse, v. So we have 5 squared plus negative 31.8 squared equals v squared. V is the square root of that mess. Which is 32.26. And again, we have 3 significant digits in the given data, so 32.2 with that 6. V then would be 32.3 meters per second. So that gives us the magnitude. 32.3 meters per second. Now let's see if that makes sense. We said the impact velocity must be greater than either the vertical, if it had just been dropped, or the horizontal. And that's true. We end up with 32.3, which is greater than this. This is the resulting velocity, 32.3. But all vectors have magnitude and direction. We know the magnitude, now it's time for the direction. Now we now know all 3 sides, but this one is given, so that's the one we should definitely use. This one we obtained by doing 1 calculation. This we involved by doing 2 calculations. So it is a little bit safer to use this value this one and this one than say this and this, because this is given. There's no chance there's a mistake. If we made a mistake here, and there's carry through. So we're reducing our chances of mistake by using these two sides. So this is the opposite, that's the adjacent, and that gives us tangent. So we have tangent theta equals opposite over adjacent, which is Vy over Vx, and so then theta is the inverse tangent of Vy over Vx. And this is, again, a good reason I stored Vy, so I can use the unrounded value. So the value that comes out is negative 81.084 degrees. So in this context, what we know is this is 30-some, and this is 5. So this is like 6 times longer. It's not drawn to scale, so 6 times longer would be off the page, and you can see that that then is a very big angle. So this angle theta, this negative 81.08, which should be rounded 3 significant digits to negative 81.1 degrees, is, on the coordinate system, an angle swung this way. It is swung southward from east. Negative 81.1 south of east. So overall, the velocity is 32.3 meters per second at 81.1 south of east. And of course, if we do negative 81 south of east, that's confusing. So we want to leave it positive. Negative 81 south of east would mean actually going into the northeastern quadrant. So we want to be careful of that. We interpreted negative. This negative means south of east. So we can't have negative and south of east in the answer. And so that's how we could use two vectors and the components to solve a particular problem. The next example we want to consider is when we have multiple vectors and we're adding the components. So now we have our boat that we saw before, 13.8 meters per second, 52.6 north of east, and a current is flowing 4.65 at 23.4 degrees north of west. So let's see what we're dealing with there. Previously, you saw that I could draw this vector here, like so, in this particular place. And that gave us this vertical component, like so, and this horizontal component, down here like this. So we have our Vx and our Vy, which we solved in an earlier example. But now, from an addition perspective, we have a current that's flowing at 4.65, so it's about a third as long, at 23.4 degrees north of west. Let me just put this angle in here so we have it. Theta is 52.6 degrees. And this was V at 13.8. So now we have a situation where the vector is, adding them graphically, I would go to the end and I would look for 23.4 degrees north of west. So here's west, and 23.4 would be in this direction. So I've got 3.4, like so, and 54.65 is about 1/3 this size, so I'm not drawing it to scale in this drawing. I'm just trying to give myself a semi-accurate sketch to do some interpreting. And we might be looking at a vector like that. That's probably a little too long, but we get the idea. So now we see we have a Vx that looks like this, and we have a Vy that looks like this. And this angle here is 23.4 degrees, and this velocity is 4.65 meters per second. Now, of course, the resultant overall is going to be this. So you can see the boat is trying to go this way, but it's being pushed in this direction, which results in this overall velocity. So how we solve this, and we've seen this before, is that this resultant vector is really this y and this x. Well, you can see the x is actually this positive Vx plus this negative Vx is the length of that side, and the y, this y component of the resultant, is really this y plus this y. So now let's go back and do a little bit more lettering here. So let's call this vector 1, v1. We'll call this one v2. So we have v1 and v2. Hi. So we've got v1 and v2. So this is v1x, v1y, and this is v2x and v2y. And to keep things a little bit simpler, I can draw my triangles over on the side. So let's take our v1x and v1y. And v1. And then we have our second triangle, which is v2. And this is v2x, and this is v2y. This is 23.4, and this is 52.6, like so. And then we've got our v total. Algebraically, vx total is v1x plus v2x. And vy total is v1y plus v2y. So we already know v1y and v1x that we had done earlier. And we know that v1x was 8.38 and v1y was 11.0. So we've already got those. We've already found those. So now it's a matter of us finding v2. So I have sine of theta is v2y over v2. So v2y is v2 sine theta. And v2 was 4.65 times the sine of 23.4. And v2y is 1.846737 meters per second, which to 3 significant digits, v2y is 1.85 meters per second. Let's see if that makes sense. Yes, if this is 4, the answer, it must be smaller than 4, and it's a shallow angle, so we'd expect it to be a lot smaller than 4. Now we'll do the x, cosine off this triangle, adjacent, hypotenuse. So cosine theta is v2x over v2, and v2x then is v2 cosine theta. V2x is 4.65 times the cosine of 23.4. And that is 4.26755, and V2x is 4.27 meters per second to 3 significant digits. Now, of course, we want to work with the unrounded values, but that's what we end up with. All right, so now let's go back up here to V2x. Now, V1x is positive 8.38. And V2x is not 4.27. This is where we have to be careful. It's in the opposite direction. So it's actually negative 4.27. So this is minus 4.27. We use the unrounded value for V1x. And we end up with a Vx total of 4.11422 meters per second. So Vx total is 4.11 meters per second. Now our scale doesn't seem to indicate that. Again, this is not a scale drawing. If you look at this, you don't say, oh, obviously that must be 4, the difference. This being 4.65, I actually drew it way too long for this particular scale. If this was about 14, it should have probably been like this. And then you can see it would be about halfway. But in either case, we have our x total, and now it's time for the y total. V1y we know is 11.0. And V2y is 1.85, and that is in the positive direction. So that's plus 1.85. Plus the unrounded value of 10.96292 gives us 12.80965 meters per second. 3 significant digits. Vy total would be 12.8 meters per second. So now, what do we know? We know we have our final resultant triangle, which looks like this. And we just determined that this x, Vx total, is 4.11 meters per second, and Vy is 12.8 meters per second. So now we need to find this angle V, and we need to find this angle. We need to find the magnitude of V and the angle. Well, we have two sides, so we can use the Pythagorean theorem, as we did previously. A squared plus b squared equals c squared, and that is Vx squared plus Vy squared equals v squared. So V then is the square root of 4.11 squared plus 12.8 squared. And that gives us a velocity of 13.443 meters per second. Gives us that velocity. So now we know this is 13.44. And now we need to find the angle. These were the two primary numbers we have, so we'll use tangent. So tangent theta is Vy over Vx. Theta is the inverse tangent of 12.8 over 4.11. And that gives us an angle of 72.19 degrees, which would be 72.2 with 3 significant digits. So that's the angle. Now looking at the angle here in our drawing, we can see, all right, the angle, this has a vertical of 12. This has a vertical of 12 and a short horizontal. So this angle is going to be big, 72.2. Well, this is the easterly direction, and that's the northerly direction. So we're looking at north of east. So 72.2 degrees north of east. So overall, the resultant velocity's magnitude is 12.8 meters per second at, is 13.434 meters, 13.44 meters per second at 72.2 degrees north of east. 72.2 degrees north of east at 13.44 meters per second. So that's how we'd resolve that. So I just want to talk a little bit about theory, to clear up a little bit of theory here so there's no confusion. Both the IB data booklet and the Regents reference table show these formulas for dealing with vectors. I don't like them, obviously, because I'm taking the time to do it, and I showed you a different way. Notice the diagram, first of all, is parallelogram method, which we don't like to begin with. We just don't like that to begin with, parallelogram method. The second thing, which we want to take note, is how we would draw this to resolve it. So first of all, we would have our vectors like this. So this would be our, let's say, our velocity, and this would be our Vx, and this would be our Vy, and this would be our theta in this particular problem. So let's set about finding Vx. If we know V, initial velocity, let's say the number was 25 meters per second. So we have a number with it, just giving you an example. If we have V and we have this angle theta, and let's say it's 31.6 degrees, if we know those two things, we can find Vx and we can find Vy, the components of this vector. So starting with Vx, let's start with Vy, actually. Vy is opposite, and we know the hypotenuse. So sine of theta is Vy over V. Vy then, cross multiplying, is V sine theta. Now, if you look at this up here, you can see, oh, this A, whatever it is equal to A, excuse me, the Y, AV. AV, the vertical, is equal to A times the sine of theta. This I find more confusing than just having a triangle and doing the trig and solving it for each particular case. So now if we do cosine theta, it's going to give us Vx over V. Vx then is V cosine theta. So what are they saying here? This A, this side is A, and this is Vx, or this is AH, horizontal instead of X, and this is vertical instead of Y. All right, so basically we have for Y, we're saying this is equal to, the vertical is equal to A, the length of this, times the sine of the angle. What are we saying with our method? We're saying Vy is equal to V, which is this vector, times the sine of that angle. They're saying the same things. I find this more of an abstraction. This is straightforward. You don't need formulas in a reference table or a picture to figure it out. Now, some of you may wonder, how does tangent come into play here? How does tangent come into play here? And there's an interesting kind of algebraic turn of events that will come about here to bring things full circle. So this is really the entirety of what we need to understand. So let's say tan theta. Tan theta is opposite Vy over Vx. So given this, we could solve for Vy, and Vy then would be Vx tan theta. And then Vx would be Vy over tangent theta. Vy over tangent theta. So it's just a way of rearranging these things. Now you may remember from trigonometry that tan theta equals sine theta over cosine theta. That should be an identity that you remember. So if we look at sine theta, well, what is sine theta? Sine theta is Vy over V. What is cosine theta? Cosine theta is Vx over V. You can see when I divide these out, these V's will cancel, and I'm going to be left with Vi over Vx, which is this right here. So the short of it is that using tangent has no value to us because anything we would know to use the tangent, we would need to know to do the sine and the cosine. Really, tangent is a composite of sine and cosine. So we don't need the tangent, except if we're finding an angle. But in terms of components, the tangent's not really relevant or helpful.